Everyone, here are a couple example bomb calorimetry style problems. Let's go for it. First one says, calculate the amount of energy gained by a calorimeter with a heat capacity of 7.61 kilojoules per degree Celsius if its temperature increases by 12.8 degrees Celsius. I think the first thing to notice is that this question, it does not specifically use the word bomb. It just says we have a calorimeter. But there's this telltale phrase, a heat capacity. Not a specific heat capacity, just a general heat capacity. That is a sign we have a bomb calorimetry style problem. And when I notice this number right there in kilojoules per degree Celsius, those are units unique to bomb calorimetry questions. To take our interpretation one step further, this is not a full-blown calorimetry style question. It's only asking us to focus on the calorimeter itself and not on the energy transfer. All of the numbers in the question relate to the calorimeter itself. Calculate the amount of energy gained by the calorimeter. It's the heat capacity of the calorimeter, and there's the temperature change of the calorimeter itself. So this is just a Q equals C delta T style question. Now this is a new type of formula. It's easy to accidentally want to do Q equals MC delta T, but those units right there do not have a mass. We're doing a general heat capacity, not a specific one. There's more than one sign pointing us toward, oh, it's just Q equals C delta T. Let's substitute. This capital C is the heat capacity of the calorimeter, pretty explicitly told to us by the question. 7.61 kilojoules per degree Celsius. And then the delta T, the temperature change. The temperature increases by 12.8 degrees Celsius. 12.8 degrees Celsius. It's a pretty short calculation. Let's do it. 7.61 times 12.8. I got 97.408. It's my raw answer. Let me go back to the question. The two values both have 3 significant digits. I'm going to round off. 97.4. Here, it's very tempting to want to put joules in there. In our other style of questions that had Q equals MC delta T, we expected joules, but here, the heat capacity is already in kilojoules, so our degrees Celsius cancel, and we're left, a little bit surprisingly, with kilojoules. There is a style of question about a bomb calorimeter that asks us to focus on the calorimeter itself. It's not about an energy transfer. All of the numbers are about the calorimeter itself. So there's a new calculation to do, but it's quite short. On the other hand, let's look at this example. A chemist burns 0.930 grams of carbon in a bomb calorimeter with a heat capacity of 9.69 kilojoules per degree Celsius. If the temperature of the calorimeter increases from 25 to 28.15 degrees Celsius, then what was the molar enthalpy of combustion of the carbon? This time, the word bomb is there. That's a pretty strong signal. And just like the last example, we have this phrase, not a specific heat capacity, a more general heat capacity. And there are those units that let us know, oh, this is a bomb calorimetry style question. In contrast with the previous example, this question gives us a number about the carbon. There's an implied second value, the molar enthalpy of combustion of the carbon. There's a number that we have and something that we don't about the carbon. And there's this heat capacity of the calorimeter and the temperature change of the calorimeter itself. So there's a language cue and something about the units to let us know we're in a bomb calorimetry style question. And this one is about the energy transfer. We have numbers about two different things. So we have negative heat gained equals heat lost. It's a calorimetry question. It's an energy transfer. The calorimeter itself is gaining energy, and the carbon is losing energy. We're expecting negative C delta T equals NH. We're being asked for the molar enthalpy of combustion of the carbon. So that's H equals that negative C delta T, but then it turns into mass over molar mass for the moles of the carbon. Let's substitute. H equals the negative. Don't forget that big negative. Capital C is the heat capacity of the calorimeter, 9.69. 9.69 kilojoules per degree Celsius. The temperature change here was from 25 to 28.15. I can do that in my head. That's 3.15 degrees Celsius. We're dividing by mass over molar mass. That's the moles of the carbon. The mass is here in the question, 0.930 grams. Over the molar mass of carbon, that's 12.01. I set up my calculation. Let's push our buttons. Negative 9.69 times 3.15 divided by 0.93 divided by 12.01. I got an answer, negative 394.1798226. Go back to the question, a couple numbers with 3 significant digits and a couple numbers with 4 significant digits. I'm going 3 significant digits. It's negative 394. Let me pay attention to my units. Degrees Celsius cancel there, leaves kilojoules in the numerator, and the grams cancel over there. I'm in the habit of expecting my molar enthalpies in other style of calorimetry questions to come out as joules per mole. And then I have the option of using scientific notation or doing a unit conversion. Whereas with bomb calorimetry questions, because that general heat capacity is already set up as kilojoules, I'm actually getting kilojoules per mole as my immediate answer. Bomb calorimetry questions might have the word bomb in them or might not, but they're always going to have some language cues, often a heat capacity, not a specific heat capacity, a more general heat capacity. Be on the lookout for numbers with those units to let us know it's a bomb calorimetry style question. From there, if we only have numbers about the calorimeter itself, it's a short and sweet calculation. In contrast, if we have numbers about two different substances, we're going to have to focus on the energy transfer. Watch that negative, watch those significant digits, watch your units, and I hope that helps.